Yeah. Okay. So last time we talked, I gave you a very sort of abstract talk about a very idealized system. So how I can understand a spin liquid in a very ideal spin 1/2 Heisenberg Hamiltonian. Usually I just wanted to put nearest neighbor interactions. And today I want to take a step back and essentially take a totally different perspective and talk about how you actually get your models that you then use to find whether or not you have a spin liquid and how you sort of look at that. So real life is generally not going to be represented by an idealized Heisenberg Hamiltonian. And if you really want to understand whether or not you get a spin liquid, you need to sort of understand this basic Hamiltonian. And you get a lot of other really rich and interesting physics out of this. And one key point is that when we're looking for frustrated magnetism, you've taken your ordering temperature of what could have been a magnet and you've suppressed it down to 0. So you tend to have a lot of competition. And so in these cases, the details often matter a lot. So you really need to think about what's actually happening in your system. So that's sort of the key point, is that the details can be important. And so what I want to talk about is how you actually connect a material and a model. And so I'll talk about it from the theoretical point of view, where we're going to imagine you're just looking at some kind of crystal structure, and you want to use this to construct what you think might be a likely Hamiltonian. This is going to be fairly high level, but please ask me lots of questions. If you want a reference, there's a textbook by Fazekas, which goes into a lot of this in a very nice way. So when we're looking at our model, we have basically two types of ingredients. We have our local moments, so whatever is happening on site. So before this was spin 1/2, and then we have our interactions. So we'll focus on sort of the interactions for frustrated magnetism, but when we talk about on-site terms, this affects everything throughout all of strongly correlated systems. So first we'll look at the on-site part. So we're going to focus on local moments in insulators where we have electrons localized on a site by some kind of strong interactions. So reality is often more complicated. Things will be close to a mod insulator. You also have magnetism in metals. And we're going to approach this from sort of one extreme limit where everything is perfectly localized, and the kinetic, and you only worry about intersite terms when you start to look at the intersite interactions. So this is not necessarily always correct, but it's actually really generally will gain you a lot of insight. So when you look at, say, the iron-based superconductors that Andre was talking about, you can initially look at them from the point of view of magnetism from this spin density wave picture. You can look at them from the localized picture. The spin density wave picture is probably more correct, but both give you sort of useful insights, and you get a sense of what might be going on. Okay, so our simplest picture of a local moment, we just have a single orbital per unit cell. We can put a simple spin 1/2 on here. This is what we use to construct the Hubbard model. This is sort of your fundamental, simplest picture, and we're going to go beyond this. But if I have this kind of picture where I have the Hubbard model with U much larger than T, your electrons become localized, you form spin 1/2 moments, and when you look at the interactions of these moments, this is how you get the Heisenberg model. And so what I want to talk about now is how life is more complicated than this in reality. So instead of having a single orbital where I didn't tell you anything about the orbital character, so you might have just assumed that it was S-wave, you have real electrons, R and D, and F transition metal orbitals. You tend to have, you can have multiple electrons per atom. You have to worry about spin-orbit coupling. And in general, there's 3 different interactions you have to consider. So Colin went through this a little bit yesterday, or maybe on the first day, Tuesday. But I'm going to just go through it again with a slightly different perspective. So these are your sort of three on-site interactions. So you have a Coulomb interaction between your electrons on a single site. This gives you also, we call this the Hund's interaction between orbitals on different electrons in different orbitals. And this gives you what are Hund's rules, which are some sort of empirical rules that often work but also often fail. And if you have multiple electron atoms, you can use these to construct your total L and S for this. The next thing that you often have is crystal fields. So for s orbitals, it doesn't really matter what your lattice symmetry is, but once you talk about d and f electron orbitals, then they can really feel the symmetry of your lattice, and this gives you an energy splitting. So essentially free space, you have an SO3 symmetry for your crystal fields, so all of your 5d orbitals or 7f orbitals will be totally degenerate, and in, say, cubic symmetry, you're going to split your 5d orbitals like this, for example, and so this crystal field energy scale gives you the scale of that splitting. And more, I'm just sort of giving you the basic sense. We'll come back to a little more detail shortly. And then the final thing to consider is often also lumped in with Hund's rules, which is spin-orbit coupling. So I represent this as lambda spin-orbit. And this is a relativistic effect. It grows with the number of nucleons in your nuclei. So it gets much, much larger as you go across and down the periodic table. And if it's very, very strong, then you end up using your total J instead of your spins. And so you're looking at these sort of total J states. OK, so why do we care about this? And that's because different materials of interest lie in sort of different regimes. So we can always try to solve the full complicated problem, but as theorists, we like to try to make life as simple as possible. And so we like to take different limits. And so if you look at 3D transition metals, like copper, then these are generally in this case where your Hund's rule couplings are typically larger than your crystal fields, but sometimes on the same scale. And these are much larger than your spin-orbit coupling because you're only up on the 3D level of your periodic table. So you can generally neglect spin-orbit coupling for a first pass and introduce it only as a perturbation. When you look at 4F rare earths, this is actually even easier because your Hund's coupling or Coulomb interaction is very, very large. Your spin-orbit is your next largest term, and then your crystal fields end up acting as your small perturbation. And then finally, we'll talk about the iridates, for example, so 5D transition metals. And this is sort of only recently people have really looked at magnetism seriously in these systems where all of these energy scales are on the same order of magnitude. OK. So hopefully you have a little bit of familiarity with some of these things, but I just want to walk you through how you would use these, and we'll do some simple examples. OK. So just to summarize what Hund's rules are, your first rule is that you want to align all of your spins. So this is all coming from the Coulomb interaction, where you want your spins on the same atom to be as far apart as possible. So if they have a symmetric spin wave function, then you're going to have an anti-symmetric spatial wave function, and they'll be further away. So you're going to maximize your total spin. And you can actually write down this Hund's coupling as an interaction between spins in different orbitals in the same atom. Your second Hund's rule is that you want to get the largest total L that is consistent with the first rule. And so there's a cheat to figure out what this is. So if I have L equals 2, I can write my different LZ orbitals. So here I'm still thinking in free space, and then I can fill them up with my spins. So let's say that I have 4 electrons in my atom. I just do this, and then I sum up my LZ here. So this modulus of this LZ is equal to 2, and this actually gives me my total L is equal to 2 in this case. And then the third Hund's rule is really this spin-orbit coupling, which tells you that J is either L minus S or L plus S for less than half filling. And greater than half filling. And for exactly half filling, your total L is equal to 0. So that would happen if I filled this up, and I would get L equals 0. And you can write this again for each orbital as a dot product of the spin in that orbital with the angular momentum in that orbital. And when you consider the total problem, that's when you get this third Hund's rule. Okay, so you can get all of these, write them down in some kind of multi-orbital Hubbard model, and basically derive Hund's rules that way. Okay, so let's see how this works. So we're going to do a couple of different examples, basically one for each of those 3 cases. So here is lanthanum manganese O3. This is in a perovskite structure, which is cubic. And I know that my manganese is going to be my magnetic atom here. So the first thing I want to know is how many d electrons do I have? So here you have to do some simple chemistry counting. So I know oxygen likes to be 2-. I know all of my rare earth atoms like to be 3+. And so to get the charge counting to work out, my manganese has to be 3+, and manganese 3+ has 4d electrons. So it's a 3d. I can neglect spin-orbit coupling to first order. It's in a cubic environment. And so here we'll take our single electron picture. So this is our crystal field picture. And this is how my d orbital split in this particular cubic structure where the manganese is sitting inside an octahedron of oxygen atoms. So what I do now is I want to fill it up according to Hund's rules. So if Hund's rules are totally correct, then I just want to align my total spin. So you see here, I'm actually only going to follow the first Hund's rule. And the second Hund's rule, actually my crystal field is larger than that. So here, I filled in all my spins. I have a total spin of 2. I have an extra degeneracy left over up here that you might want to worry about, but doesn't end up having much of an effect. And so here, this is the case when your Hund's rule is larger than your spin-orbit coupling. So this is what always happens for manganese. But just, I could have had a different limit where my Hund's coupling was smaller than my crystal field splitting, and so then you end up getting this state. So this is going to give you a spin 1 state. since you just count what's left over. And so you get high spin, and you can get different high spin and low spin states. So this never happens for manganese. It happens for cobalt and very rarely for nickel and iron. So here, you don't end up having an orbital contribution because the expectation of your orbital angular momentum in the EG doublet is 0. Here, you are going to have an leftover angular momentum. And so here, this is going to be a Heisenberg-like spin. So you're really going to get a spin 2 here. Here, you're going to have an angular momentum. And we'll come back to this when we talk about the iridates, but whenever I have a system with 2 levels, I think of this as a pseudo spin 1/2 doublet. Whenever I have a system with 3 levels, I can think of this as a pseudo angular momentum of 1. And so we'll say that this, you can say that this T2G has an effective angular momentum of 1. So you have an effective angular momentum of 1, and if you take the expectation of your L effective, this is actually exactly opposite to your actual angular momentum. So you can plug in what your actual T2G orbitals are and calculate your angular momentum, and you find that it's just basically the opposite of what you would have written it down as initially. So you do get this kind of coupling, and so you will get anisotropic moments. Okay, other questions? All right, and so what I want to talk about next is the rare earth ions. I'm actually going to just look at one material for both the rare earths and the 5Ds. So this is a pyrochlor iridate, and actually both the praseodymium and the iridium sit on a pyrochlor lattice. So I want to, and actually the iridium ends up being metallic in this case, but we're going to look at what its magnetic state would be. So let me do the spin, the charge counting. So again, I have 2 minus and 3 plus, and that means that my iridium has to be 4 plus. So both of these could be magnetic. And you really expect the praseodymium would be because the U is very, very large, whereas for iridium, U is smaller, and so it's, in this case, it is actually metallic, but in other cases, it can be insulating. So if we look at praseodymium 3 plus, this has 2 F electrons, and so now we want to do Hund's rules, and for F electrons, we know that Hund's rules work really well, so I better just find my total S and my total J first, so, or total L first. So I have S is equal to 1 because my 2 spins align. If you do exactly that same picture for L equals 3 for F electrons, you find that your L is 5 because you have a minus 3 and a minus 2. And your spin orbit then couples these together to get a J equals 4 term. So if my praseodymium atoms were in free space, then I would have 9 degenerate levels. However, they're in a crystal field environment. They're actually in a trigonal symmetry. So the praseodymium is in the center, and then I have oxygen at the 6 corners of this trigonal prism. And you can see that this has a kind of a D3 local symmetry, also known as a trigonal symmetry, but you can connect this to a particular group. And then you can look up, it's tabulated for all of these what the possible crystal field configurations are. So in this trigonal case, we get 2 doublets and 5 singlets. So singlets are going to be totally non-magnetic, and then praseodymium will be very boring as long as you're at sufficient temperatures below your crystal field splitting. And just so you know, symmetry tells you what these have to be, what your sort of possibilities are. It doesn't tell you what order they're in. So here I put my symmetry. The cubic symmetry just tells me I have a T2G and an EG. It doesn't tell me what order they're in. You can guess that by looking at the particular structure. That sometimes works. It works really well for transition metals. It doesn't work really well for rare earth ions. So usually what you'll do is actually you can measure this. And actually Colin showed you some data. So you measure it with inelastic neutron scattering. You can see these different local excitations. And so you can actually determine exactly what this configuration is. At this point, let's say we know that we have a doublet. So if you measure your magnetic susceptibility and you see you have some kind of magnetic susceptibility at low temperatures, you know you don't have a singlet. And you can, so we have some J equals 4. And we have a trigonal symmetry. And so this means that when you look at your states, their JZs are going to mix with other JZs that have a delta JZ of 3. So this comes from this trigonal symmetry. You can do something similar into trigonal symmetry. So if I start with a state that has +4, then this will mix, so let's put some configuration here. This will mix with +1 and with -2. And then that's all it can mix with. So this is the generic form. I actually get a doublet, which has 2 states which are the time reverse of one another. And what's interesting about this doublet is that it's an Ising magnetic doublet. So you can see that you're definitely going to have some expectation of JZ, but if you try to find your expectation of JX or JY, there you need something that's connected just by a change of delta J of 1. So nothing is connected here, so it's definitely only going to have expectation of JZ. So this is one of the ways that you can get away from this Heisenberg moments, and you really have pure Ising moments when you have this doublet here. Okay. Questions? Oops, where is?
Does this mean there's no interaction in the channel
So you have to be a little bit careful. Because this is only telling you about your on-site anisotropy, but so when we talk about how you get magnetic exchange, you're going to take your magnetic exchange and you have to project it down into this ground state doublet. So you can, you have to, okay, so the other thing that's important to think about in these systems is it is a doublet, right? So this is a pseudospin 1/2. And so I'm going to have some sort of pseudospin perpendicular moment, and this is actually going to be a quadrupolar moment. So it will mix, I get a mixing with states of plus and minus 1. So this is a delta L of 2. So this will give me a quadrupolar moment sort of as my first term. So you can have essentially quadrupolar interactions. But if you're only looking at the spins, it won't necessarily generate those. It could be coming from the quadrupolar interactions. Yeah. Okay. Okay. So the next one we want to look at is the Iridium. So this is in a cubic environment again. And this is, Iridium is 5d5. So I'm going to fill up 5d electrons, and in 5d, my crystal field splitting is often larger than my Hund's coupling. So the way you want to fill this up is just fill everything into your lowest T2G. So I just draw 5 arrows, and that looks very complicated, so it's much better to think about this as just having a single hole. There's just a single hole in your T2G level. So here I know that I have spin 1/2, and then it's the same story we were looking at before when we had essentially one sort of extra down electron there. So here I have, I can think of the triplet as an effective angular momentum of 1. And so now I'm going to be coupling this spin 1/2 with this effective angular momentum of 1. And actually, Hund's rules with the spin-orbit coupling still work the same for this, except I'm thinking of a hole instead of a electron. So what you get is that you end up with a J effective of 1/2. So here I'm just using this fake angular momentum, but real spin. You can then connect this to what the actual, you can actually calculate what the angular momentum in this particular state is, but it's better to think of it as a J effective 1/2. Yes?
How do I think about the L effective and how do I determine?
I mean, it's 3 states, right? So one of them is L effective +1, one of them is L effective 0, and one of them is L effective -1. And you can label them how you choose, and there is people will typically choose the same convention. So people typically choose the convention such that if you calculate expectation of L in your states, it's going to be opposite to the expectation of L effective in the way that you defined your L effective. Okay, so another way to look at this is just from a single electron picture, where this is my these are my levels for spin-orbit coupling equal to 0, and I can then turn on spin-orbit coupling, and remember that each of these levels is actually 2-fold degenerate, so there's really 6 levels here. And so when I split it, I end up with doublet and a quartet. And really, whenever we see a doublet, we can think of it as some kind of effective 1/2 angular momentum. And whenever we see a quartet, we can think of it as an effective 3/2 angular momentum. And then we're just putting our single Iridium hole in this excited J effective 1/2. So what's nice about this picture is that you can actually just write down this single particle Hamiltonian and diagonalize it, and then you find out what your ground state is. So these T2Gs are your XZ, your YZ, and your XY d orbitals. And so you're going to end up with a linear combination of your 3 different T2G orbitals. It's got some imaginary components. You have a plus spin 1/2 here and a minus spin 1/2 here, for example, and these are your 2 time reverse states. So once you write down your ground state doublet, whenever you get your interactions, you can always project them down into this kind of ground state. Okay, so this is essentially you can do more complicated things on a single ion, but it's all going to be essentially the same thing. You can always write down your full Hamiltonian for all of your states and diagonalize it and find your appropriate ground state and excited states. Okay, so what we want to consider next is magnetic exchange. So in the very simplest picture, whenever we have spin and half, we have some kind of dipole-dipole interaction. Typically, this is going to be very, very small. It does show up in some spin ice materials where you have very large moments and otherwise small energy scales. But most of the time, your magnetic exchange is going to be coming from the Coulomb repulsion. So the simplest thing you can get is direct exchange. So when your wave functions at different sites overlap, then you want to look at your actual total wave function of your two electrons on these two different sites. So if my electrons are in a spin antisymmetric combination, then I'm going to have a spatial wave function that has no node in it. And if they're in a spin symmetric configuration, then the spatial wave function is going to have a node in it. And so direct exchange, since the Coulomb repulsion wants my electrons to be as far apart as possible, that gains me energy. This is going to give me a ferromagnetic exchange. Okay. This does require direct overlap. And so in a lot of 3D transition metals, you don't have any direct exchange. In some of the 5D transition metals, you will have direct overlap, and then you have to consider this. And the reason for that is essentially that 5D wave functions are much larger than 3D wave functions because they have a lot of spatial nodes in them. So 4F wave functions are also similarly small, and so you won't tend to have a lot of direct exchange. The standard exchange in insulators is super exchange. So you can sort of see this in the simplest sense if I have a Hubbard model. So we'll just look at two electrons sitting on sites in my Hubbard model, and they're allowed to hop back and forth, but they're penalized for having any double occupancy. So when u is equal to infinity, there's absolutely no hopping, and I have a total spin degeneracy 2 to the n for n sites. But if u is not infinite, then I can have essentially virtual hopping processes, where this electron can hop over here, and then it can hop back. And then via second-order perturbation theory, I gain some energy that's on the order of t squared over u. And so this is always an energy gain. As long as you can move, you gain energy. But the only way that you can move is if you have electrons with two different spins, right? If you have the same spin, then that's Pauli blocked, and there's no way for it to gain energy that way. So essentially, it gains energy if the total spin of my two sites is 0, and it does not gain any energy if my total spin of my two sites is 1. And so you can just write, so you've looked at your energy gain, and then you can just say, well, my Hamiltonian is essentially equal to this energy gain times the projector that I'm in a spin 0 site, which is going to be just an it will end up being an anti-ferromagnetic exchange between my two spins because I want them to be anti-aligned. Okay, so this is a very simplistic picture. It doesn't usually happen this way because usually electrons hop through intermediate oxygens. And that's useful to understand because if I look at this simple picture, I can only understand antiferromagnetism. There's no way to get sort of a ferromagnetic exchange from superexchange, or from that kind of simple version. So superexchange really typically involves hopping from, say, a copper 2+, which is a 3d9, which we'll typically think of as sitting in the dx squared minus y squared orbital, through an oxygen to another copper 2+. So this hopping is going to involve, so if I'm along the x direction, it's going to involve the px orbital. And again, so here life is more complicated. And okay, so you can hop all kinds of ways. There's some intermediate energy cost if you have both of your electrons on the p orbitals. There's energy cost if you have both on the d orbital. So it's a more complicated problem, but you can work out all of the different essentially superexchange paths where your spins can hop from one electron and then back to your initial ground state. And you'll see that this is still antiferromagnetic. So it's not exactly zero energy for the ferromagnetic alignment, but again, you'll get antiferromagnetic alignment. And so you can calculate some kind of J for this flat 180-degree angle. So what's more interesting is if we now have a 90-degree angle. So here is my 2 copper atoms, and these will hop. So this one will hop to a py, and then the other one will hop to a px. And so the intermediate configuration on the oxygen atom will actually involve 2 spins in different orbitals if I hop from here to here and from here to here. And when they're in different orbitals, we know they have a Hund's interaction, and so this is going to favor a ferromagnetic interaction. And so if they're exactly at this 90-degree angle, you're going to have a ferromagnetic interaction. And generically speaking, your angle is going to be neither 90 degrees or 180 degrees, and you have to consider basically both types of hopping terms. Okay, and you can get your J's for different paths. So if you're looking at any given crystal structure, you can see where your transitional metal ions are, you can see where your oxygens are, and so you can look at the different superexchange paths and you can estimate what J's you think are present and roughly what orders of magnitude they are and what signs they are. So this is a sort of a useful tool for getting a rough sense of what kind of model you might get. And all of these so far, however, are giving you Heisenberg exchange. And the key point to remember here is that the only thing that is hopping are single spin 1/2 electrons. So essentially only your spins hop. So all of your angular momentum is stuck on site. And so you have to essentially, we can get anisotropic exchange by considering how this kind of superexchange gets projected down into our strange ground state doublets, like the J effect of 1/2. Okay, so that's Okay, so there's two ways that you can get an isotropic exchange. The first way is that you can essentially get extra terms in your super exchange. So here, when we looked at our hopping term T, this is essentially when you do your Hamiltonian, that's in your numerator of your super exchange term. This is going to be your hopping term here. So you can also get terms where you have your spin-orbit coupling as an intermediate term, and also maybe some hopping terms. And so this will give you a term that goes like lambda spin-orbit. And so what you can get are terms that are in perturbation theory on the order of lambda spin orbit times j squared, lambda spin orbit times j and lambda spin orbit times j squared, and potentially higher order terms. The other way is what I already talked about, which is project your spin-spin hopping results into your ground state doublet, or whatever multiplet you're looking at. All right. So this becomes very complicated. You can always write down exact matrices where you consider, say, the two-site problem, and you know what your hopping is, you know what all of your different energy levels, initial energy levels, costs are, and so you can write a big matrix and diagonalize it. And so it's useful to look at what the most generic thing that you can get is. So we'll look, still it's pseudospin 1/2. On just a site where I have two different atoms at sites I and site j. So my bond between sites I and site j no longer has to be a Heisenberg type form. So I can write it generically as a matrix in my spin indices. So we'll typically rewrite, and this is going to be not our true spin, but this is our pseudo spin. So for the iridate, this would be your J effective of 1/2 degree of freedom. So we'll separate, this is typically separated into 3 different types of terms. So the first is a diagonal exchange. And there's 2 cases that you should be familiar with. If all of the J's, A's are the same, this is your Heisenberg exchange. This is also where you'll get something like an XX Z model. So even if you have a pseudospin 1/2, you can get just anisotropic exchange by projecting your super exchange into the ground state. And then the Kitaev model also fits into here because that's for any particular bond, you're going to have just some SAI, SJ, SIA, SJA, for where this will depend on your particular bond. The next term is, our next 2 terms are going to be off-diagonal exchange. So I don't have, okay, so this is going to be what's called Zhaoshinsky-Maria. So D here is a vector that's going to depend on your bonds. Yes?
Yeah, I just had a I wanted to just ask clarification for the Kitaev model. For the honeycomb, I understand it's XX, Y, Y, DT, depending on the
right.
relation. But for generic cases, what do you mean by that expression?
So this is, here I'm just looking at a single bond. So on a single bond, so I'll write down the full Kitaev model, but on a single bond, it's essentially just an Ising coupling. But you then have different Ising couplings for different bonds in your lattice. So Joule-Lipsky-Marie is an off-diagonal anti-symmetric exchange. And this comes in at the order of your spin-orbit coupling times J. So it comes essentially from a term in your generalized superexchange that looks like this. And this is, you can see that this is a pseudo, that D is a pseudo vector. And so D is only going to be allowed if you have a non-center symmetric material. So this will typically be smaller than J for 3D transition metals where your spin-orbit coupling is small, and this is typically where you'll actually look in this term. Yeah?
So even if I have an inversion symmetric material, but I have a complicated unit cell so that S, I, and Sj are not all inversion centers. Or
Right.
there is an inversion center between them. I can still have d between individual spins, right?
Yeah, so it's a non-center symmetric bond. I believe that's correct. Okay. Right, and then the final term is symmetric exchange term. That's off diagonal as well. And what you're typically going to do in a material is use symmetry to reduce this Hamiltonian where you have 3 parameters here, 3 parameters here, and probably 6 parameters here, and reduce this by symmetry and looking at how different bonds transform to one another. This is everything for spin 1/2. If you have higher spins, or say triplet ground states instead of a pseudo spin 1/2, then you can have additional terms like single ion anisotropy, biquadratic terms that are involving, say, Si dot Sj squared. Or you can have, if you have more sites than just 2, then you can have something like ring exchange, where you're essentially flipping spins as you go around, say, a square plaquette. And all of these things will come out of a super exchange-like picture. Yeah, so 10 minutes, yeah. All right, so okay, so I just want to mention before we talk about what you do with all of this, just the one particular Kitaev model, which is coming from the J effective 1/2 state. Okay. So I mentioned the Kitaev exchange because this is particularly important these days since the Kitaev honeycomb model is exactly solvable, and people are starting to look at materials where you wouldn't necessarily have written it in terms of a Heisenberg Kitaev exchange of spins, also using this model. So just okay, so if you have sort of 3 bonds coming out of a site here, what the Kitaev model is that you'll have an XX exchange on one model, one bond, a ZZ exchange on the other bond, and a YY exchange on the third bond. And so the honeycomb picture is complicated, but for a triangular lattice, you can get, it's a little bit easier to draw. So if I have 3 particular sites. So this is the honeycomb. So here I have 3, say, J effective 1/2 sites, 1, 2, and 3. And then I have oxygens here at all of these intermediate cases. So here you can use this to basically do super exchange through the oxygens. And use this essentially to derive your Kitaev exchange. So it's really just coming from super exchange. It's nothing more complicated. Yes? What do you mean anisotropy in the Heisenberg? Right. Why? Well, so anisotropy will come from, this is, okay, so if you just have spin 1/2, then you don't have, you have a purely Heisenberg term. If you have, say, an Ising magnetic doublet, when you project your spin-spin hopping down into that doublet, you essentially, your spin-spin hopping does not take you, does not generate terms that look like, say, an SX in your pseudo-spin 1/2. And so you really just won't have that term there. Or it will be much, much smaller than your JZ. And then this is totally going to change your physics, because everything we looked at the first time was for SU2 symmetric models. So generically speaking, you don't have SU2 symmetry in your exchange terms. I mean, you can have, yeah, so like if you have something like a tetragonal symmetry, then it's easier to get an Ising magnetic doublet. So, but when you look at the Kitaev exchange, you're looking at cubic symmetry still. And so you have this T2G, that's in cubic symmetry. But you have this J effective 1/2 that still ends up with a anti-symmetric, or sorry, with a anisotropic term, and that's allowed because then when you look at one bond, it will be anisotropic, and then you go to other bonds and you get your other components and restore your cubic symmetry. Okay, so I'm running quite a bit behind where I had hoped to be, but this is the basic idea. So you have a Hamiltonian. You have here we've just sort of estimated what we think the Hamiltonian might look like by looking at some crystal structure. And then we want to know what happens. And then you want to know, okay, does this Hamiltonian really fit the material that I'm trying to model? So when you're looking at a particular material, the easiest thing to look at is the symmetry. So you know the generic symmetric form of your symmetry form of your Hamiltonian. In order to actually match things, you need to solve this Hamiltonian. So how do we actually go about doing this? So I'm not going to give any of the details. But the first step is you're going to look at the classical solution. So most materials will order. Pretty much almost every magnetic model will order. And so the classical solution gives you a good sense of what might happen there. So you take S to infinity, and that whole Hamiltonian is no longer quantum mechanical. Your S are just vectors, right? And so then it's all really just a classical linear algebra problem. If you have a Bravais lattice with a Heisenberg Hamiltonian, it's very easy to do this. So you start off with something like this Jij, Si.Sj, and you just Fourier transform this. So this will become sum over Q vectors, some J of Q, S of Q dot S of minus Q. And the way that you minimize your Hamiltonian is to find your minimum J. So your ground state, if you were in one particular Q vector, your ground state classical energy is just proportional to this J of Q times the total length of your vectors squared, so your total spin S. So for many cases, this is totally sufficient. If you're on a Bravais lattice, you can just minimize this, and you already see some interesting physics here. Okay, so I can use this. Here's my minimum J. I also want to know what my S of Q looks like. And in this simple case, so these are just going to be planar spiral structures. Sorry, this should be. So I'll have some cosine of Q dot R in one direction, say the Z hat direction, and a sine of Q dot R in another direction, say the X hat direction. So I'm going to get generically a planar spiral configuration. And this is all that you can get for these Bravais lattices. You can solve for your J of Q's for different configurations of your J1s, and this you can get transformations between different states. So if we look at the square lattice, and I should wrap up. Okay, so I'll just say this. So I can take a square lattice and I can put a nearest neighbor J1 and a next nearest neighbor J2 and take them both to be anti-ferromagnetic. And then I can find this J of Q and I can solve this to find what my minimum solution is. So if this is J2 over J1, in this classical picture, I have a nail lattice below J equals 2J1. And then, so this is a Q equals pi vector. And then above, I find a minimum at two different places. And so you have to, so here there's a single Q vector, I get a single state. On the other side, I get two different Q vectors and I get two different states, which then you can have solutions that are any sort of linear combination of these in principle. Okay, and here is where you might want to look for a spin liquid. And then I think I should stop here because I'm running over time. So if you have other questions of what you might want to do next and how life becomes more complicated when you have, say, a non-Bravais lattice, come ask me at lunchtime. So thank you.
So will the notes be posted?
I will post the notes, yeah.
Okay, so the notes will be posted online as well if you want to read more. So we have time for a few questions. Okay. Well, it's been a long week. So I think oh, excellent.
So when you did the, for the cupids, when you did the hopping
Mm-hmm.
perpendicular direction, so you labeled it as J90.
Yes.
But the copper atoms are actually at 45 degrees with each other.
Right, but they're hopping through an oxygen at 90 degrees. So
what was the phi that you took with respect to?
right, so you have to look at the actual super exchange path, right? So here's your copper, but it hops this way. So if it hopped directly, right, from copper to copper, that would be 180. So if there were an oxygen here, that would give you one contribution, and then this would give you another contribution. So generically speaking, you'll have essentially where this is your coppers, this will be your angle phi.
Okay, here and then.
About, I mean, they're all just orbitals, right? So you you can always, so here we just looked at dx squared minus y squared and oxygen p, but you can draw it with any orbitals, and so any different d orbitals, any p orbitals. If you have other kinds of orbitals, you can do the exact same thing. And the generic sort of arguments are given in these good enough Kanamori rules. So, all right, there was one more question, I think. The off-diagonal, wait, sorry. Yeah, this term. Yeah, so this term should be there. There just wasn't room on the board. And this is important in some of these Kitaev materials too, because it is generically there, and you have to worry about it when you're looking at what's actually your actual order is. Right, so here you're considering your T2G orbitals. So these are your XZ, YZ, and XY orbitals at each of these sites. And they're hopping through oxygen p orbitals, which are all px, py, and pz at each of these sites. And so you have to consider all of them. And so when you're doing your superexchange, you're going to end up with a very big matrix, which is involving all of these orbitals and spin up and spin down, all of these orbitals and spin up and spin down. And note that this can hop both this way and this way. So you have to include all of these terms. You get a big matrix, and you diagonalize that, and that gives you your energies. And then you use this to figure out how you rewrite that energy, reproduce that energy splitting with a spin-spin Hamiltonian term.
About this super exchange, I want to know when the degree is 180 degree, is there some ferromagnetic situation?
So if you have 180 degree, yeah, so it can be a ferromagnetic situation depending on the orbitals. So if you have something that looks like this, hopping to, say, an oxygen and then along to another version of the same. So here, before when we drew it, this lobe was totally aligned with this. Whereas here now, this is going to be plus, and this is going to be minus. And so you have to consider, you have to be more careful, and that will actually give you a ferromagnetic exchange. So this is, again, if you look up the good enough Kanamori rules, you'll see the discussion of this there. Right, so you have to look at higher terms. I don't remember exactly where it comes from. But so there will be no direct overlap between this and the oxygen p orbitals. But you will get higher order terms in perturbation theory.
Okay, let's thank Rebecca again for a nice pedagogical talk.